as introduced here, my name is Kamil. I came from Poland. I used to be software engineer at Sentry, which is funny because when I sent this talk, it was meant to be for like Sentry, and it actually uses Sentry a lot during this talk. But you can still imagine that I work there. I love them very, very kindly. And they were doing, they are still doing, error tracking, performance monitoring, and session replay, all kind of stuff about tracing. If you have any questions about Sentry, I can still answer them. I worked there for over 6 years. First 4 years, I was working on JavaScript SDK, which I wrote. So if you have any problems with it, let me know as well. Although it changed tremendously. And afterwards, for 2 years, I was working on the processing team, which is on the other side of the spectrum. So I was consuming source maps, consuming other debugging informations from different environments. So that's it. I'm not there anymore. However, I'm right now lead of integrations at Supabase. Technically not yet. I started Monday, but you know, like if you need to integrate with Supabase, just let me know. I'm also core member of TRPC, which is type-safe way of creating end-to-end APIs. And I'm also T39 delegate. And if anyone of you do not know, T39 is like the official body that improves the JavaScript as in language. And the problem is that source maps are the bane of my existence because for all the 6 years that I've been to Sentry, they just, well, I could actually have nightmares about them because they never work. Which brings me to the alternative question, why it's so hard to get them right? First, we'll go very, very quickly about source maps as the format, what they do. Source map is a way of of storing information about what was the original source of your code and what is the processed version of your code. And it stores a way of reversing this process. So for example, if you open DevTools and you see that there is an error on line like 1 column 17,000, source maps actually are used to make this process reverse so we can understand where this code lived inside the original source code. It's used for transpilers. We have this for TypeScript, Dart, ClojureScript, CoffeeScript. Any language that transpiles down to JavaScript is definitely using source maps. And you are using source maps everywhere on daily basis, whether you know it or not. Like this is what enables you to see actually like real nice error messages. All the bundlers produce source maps, and all the minifiers, so like uglifier, terser. It's also used right now if you are using different languages. So if you are using Rust, for example, to create a WebAssembly, this is also what's used to make this process way better. Technically, there is nothing more to source maps than just JSON file, which is one of the quirks and one of the problems because there is nothing that make them stand out. It's just JSON file. The important part is that you have this mappings value, which encodes how it was processed, like what happened to your source code, that you have this vendor bundle or your application bundle, in a single file, let's say. It also contains the information about the original names of the functions, about the original source code, about the files that it includes in the bundle. But the problem is that they are all optional, and you should keep this in mind because this will be also a very, very big problem in the future. Oops, twice the same slide. Yeah, that's fine. Once you have the file, once you have the JSON file, you need to tell the browser or any other tool how to choose which file to link to the source map. So there are two ways of doing this. If you ever opened the bundle JavaScript file, at the very bottom, you've seen this source mapping URL comment. This is the link that points to the source map itself. So if you open DevTools and you see nice code, but you actually serve like bundle.js, min, whatever else, extension is there. If there is a comment at the bottom, this means that the DevTools actually use this file to make the reverse mapping of this. If you need alternative way, you can use HTTP headers. This is useful for like edge functions or if you want to override the source map itself. Once you have those two files married together, instead of seeing this, like line 1, columns 1700, something, you see this nice error which says fetch user data on line 17, column 2 in this specific file, like API. Funny enough, React, like I believe most of you use React here. React DOM till last month, I believe, or even this month, do not have any source maps whatsoever. Like they do not ship source maps. And it's only thanks to work of Marek Eriksson, who provided them as a third party. So there is a tool that allows you to see very nice React DOM names like this. This is a section that's very, very dense. So please focus if you can, because there will be a lot of bits, numbers, and stuff like this. So what are we going to do is describe what the heck is this. This is 8-bit number. The base64 encoding means that, and what is VLQ we'll talk in a second. Base64 means that a value can be encoded in 64 different values, meaning 64 different ASCII characters. So it's ABC, lowercase, uppercase, some dashes. There is a set of 64 characters, and each bit can be, each byte can be encoded as this letter. That's why if you see the mapping which says AACA, it means that there are 4 different tokens, like A is one value, A is second value, C is third value, and so on. So how does this actually work? We have 8 bits. So for example, if you have letter A in base64 is 0, so you'll have 0. But C, for example, is number 3. In binary, it would be 0, 0, 0, 0, 0, 1, 0. So this is like the encoding. The very specific thing about this encoding, though, is that the last one, the last bit, is what sets the sign of the value itself, so it can be negative or positive. And the 5th bit of the whole value is something which is called continuity byte. We'll talk about it in a second. Now, why is it VLQ? VLQ stands for variable length quantity, because those mappings can have either one value, and in this format, it will only encode the processed column number. So this is the only value that we ever store and that we ever created. It can have 4 different values in a single token. In this way, it will be column number, index, into the sources, meaning the sources as the files, the file that was used to produce this encoding. Original line number and original column name. This is the second way of encoding. And the last one is 5 different values. The additional one is just the name of the functions. For example, instead of X, you'll have, I don't know, get user data or something like this. This is the mapping. And you need this specific value in order to make this link between those values, this minified value and the original value. This is why it's variable length quantity. This is single quantity, this is 4 values, this is 5 values. And the format itself has to handle all of them. Now, the speedrun, how it works. We have whole line of mappings. It can be like in tens of thousands, it can be in hundreds, thousands, it doesn't really matter. Every single token, which is denoted by either comma or the semicolon, is a single token. The token is placed in your code. Think of tokens as the smallest possible section of the code that you have. You can have function keyword, you can have name, you can have brace, closing brace, you can have parentheses. Those are all tokens, and they are encoded in the format itself. And every value is the delta between the previous one and the current one. So instead of just wiping the state machine each time, you just add those values on top of each other until you see the semicolon, which moves to the next line, because every processing is done line by line. So we process line 0, line 1, line 2, line 3, line 4. So when you see the semicolon, you just wipe the state machine. And we'll go through this example very quickly. We have this mapping. The state machine is 0 and all nulls. So we have no values whatsoever. We have no idea what source map is containing. The first value is A. It's in base64, it's 0. So the value of in binary is 0. So what we do is we add 0 to the column number, because the first value, as we know from this slide, the first one is column number. So we add 0 to the column number. Another value is also 0. The second value is the source index, so we increment it by, well, we set it to 0. Second value is C, which in base64 is number 2. In binary, it's 1, 0. But remember that the last one is the sign. So it's literally plus 1. This is the value itself instead of 2. So we update the original line number. the last token, the last value of the token is also 0 because it's A. So the token that we have in the end is 0, 0, 0, 1, 0, and 0. This is the format. This is very, I know that there's a lot of information, but this is how it works, literally. We move to another token because we've seen that there is a comma, so we move to another token. But we keep the state machine intact. We do not touch the previous values. S in base64 is 18, which means that it's 1, 0, 0, 1, 0. This is the value that we use. We trim the last 0 because it's a sign, so 0 means that it's the positive. So 1, 0, 0, 1, in binary, it's 9. That's why we add 9 to processed column number, because this is the first value. We do the same operation for second value, for third value, which are all zeros. Then we have S again, which is, as we already know, 9. So we add to column number 9. And we have no information, sorry, we have actually information that the index is 0 now, because this is the fifth value. So this is like the last variant of this VLQ encoding. And we have token, which is 090190. And we store it somewhere in the memory. Now we have semicolon, so we wipe the whole state machine. We are back to square one. And this is when this continuity bit comes in. And this is the most complicated part in the whole format, in my opinion. We encode letter O in base64 as number 40. Number 40 in binary is 101000. However, the sixth bit, the green one, this is the continuity bit, which means that we have number which is larger than the one that we can fit in this format. Just please continue. Just do nothing. Just store this information. Just move forward. So we move to the B. B is number 2 in binary, in base64, which means in binary it's just 0, 0, 1. Sorry, I messed up something. It should be value, sorry, B is now a value 1. It's not 2, it's value 1, so in binary it's 0, 1. And now what happens is that because we had two numbers, we have to somehow carry the previous number to this value. So we take the 5 bits, because they are the most, so-called the most significant bit of this format. We take the old number that we had, and we squish them together. So together, this is the value that we have. In binary, we don't have to know what this binary is number right now. We get rid of the last bit, because this is the sign, and we are ending up with 10100, which is the value 20. That's what we add the column number, and we process the rest of the values, which is 0, 3, 13, and 0. And this is the whole format, and we have tokens now. I know this was a lot, but we are already past this. Now we have 3 tokens. What can we do with this? Because all the tokens are sorted, we can use any algorithm to find the most matching token. Meaning that if we are looking for something which is on line 0 and, in this case, column 9, we go through the tokens, we split them in half, and we are trying to find the best match, because this is how the binary search works. But basically, if we know the minified column and the minified line, meaning those first two values in the token, we can basically go through the tokens and find the one that we have. And for example, this last token, which is 120, meaning the minified line 1 and minified column 20, we know that the original thing that actually pointed to this thing is index 0, meaning that it's in file, which is stored in an array at index 0. It's line 1, it's column 6, and the name of the original token, probably just a function name or something like this, it's at index 0 in names array. If you want to know more about this format, a friend of mine, Arpad, wrote this great blog post. It's very, very dense. Okay, so we know how this format works. So what's the problem here? Like, how can we use it, and why this talk is about the problems with the source map itself? We need to understand what is ad hoc and post hoc debugging. Ad hoc debugging is when you open DevTools. You open DevTools, you know exactly what sources are used within the code. You see some error, you can click on the index.js or bundle.js, whatever that is, on the right side, and you know exactly what the code was used. There is no other way that different code was used at this specific point, because there is like the memory in your Chrome or in your Firefox, in Safari, whatever, and this code was loaded. And we can perform any sort of operations of like reversing those mappings when you are debugging. So we can show you great error. However, the problem is for post hoc debugging. What is the post hoc debugging? It means that you are trying to debug something that already happened in the past. Meaning that if you are using Sentry, for example, you configure your SDK in JavaScript, there is an error throws, and the error is sent to Sentry. And now Sentry needs to somehow figure out, let's say that you didn't open Sentry dashboard in like a week, right? And now after a week, Sentry needs to figure out, okay, what was the code that was using here? Like, how do I exactly know? Because, well, you could basically just, redeploy your app and change the code in the meantime. So if we fetch the source maps, there will be 4 completely different bundles. When this happens, all the numbers will be completely out of sync. There is no point in even trying to merge them together. Or if you are using something like Gmail or any other app that's long-standing, you probably have this in the pinned tab, open for like a month, and in the meantime, someone redeployed the whole Gmail, and the error happened, and all of a sudden what happens is that the error is using completely different code that you had in the memory. And Sentry knows about code from the past, basically. And we somehow need to figure out how to marry them together, or how to find out what was the code that was actually used. And the problem with source map is that source map, because the spec is so sparse, and we'll see this in a second, there are so many different ways. You can have source maps in a standalone JSON file. You can have JSON file, which is encoded as base64 and stashed at the end of the JS file. You can have base64, which is hosted on a completely different third-party server. And the whole format of source map is completely optional. The only thing that's like mandatory is the mappings field, like all the names, all the files. Everything else is optional. So you do you, like if it works, it works. If not, story, right? So this is the problem, and we'll try to go on the journey. What's the problem first? The first one is lack of identity, meaning that if you have JavaScript file bundle.js, and at the very end you have this comment which says bundle.js.map, how do you know which file? Like, it's just name. It's bundle.js file at some path. You may use something like there are plenty of people who think like, oh, we can use hashing, right? So instead of having bundle.js map, we have some hash.bundle.map.js. Cool, but it doesn't really work, because current bundlers are way too smart for this. And what happens is you can have, for example, you can go into the original source code, you can add comments, and the bundlers will trim the comments. So the original source is different, but the map, the corresponding bundle, will be exactly the same. And now you are completely out of sync. There is no way to tell which file was used. The same goes for something like squashing functions together. So if you have functions foo and functions foo again, like underneath, the bundlers can decide that they'll just change names. And this is the same bundle, but all of a sudden, it's completely different naming. So there is no way to make sure that this file that you think it's actually the file that you are using. So here is how Sentry works right now. You have a bunch of files. You have bundle min.js and the corresponding map. You have vendor file and corresponding map.js. You use the CLI or the plugin for Webpack, ESBL rollup, Vite, whatever bundler you are using, and it's sending it to Sentry, to the server. You need to tell us what is the release. It's completely arbitrary name, so you can use something like the current date or the git hash, whatever it is. And this name is something that can be treated as like the bucket for files. So I have my production distribution, I have my local distribution, I have my staging distribution, stuff like this. This is all the things that you need to do as the developer. And now, in theory, what happens? You have this error, which happens. Object X has no method subscribe in some TRPC bundle. You go to the first frame. You have the full URL. We do not care about the host name. We get rid of the host name. We have this. We have assets bundle.js. So now Sentry needs to think and go and think like, OK, where this assets bundle min.js live? So you are a great developer. You have this project structure. You have source. You have this front-end bundle min.js. You go to your root of the project, use the CLI. You upload all the files at once. Great. Like, let Sentry pick whatever it is. However, if you compare what happened now, is that the assets bundle min.js that you are looking from the error itself is nowhere to be found. There is no assets, there is no front end, there is no this. There is a mismatch between what you uploaded, like the path to the file, and what server seen when the error actually happened. So what you need to do is you have like this front end, you need to get rid of this. So you tell the CLI plugin like, okay, let's remove this prefix, but we need assets, so maybe add this prefix. And you're just trying to mix and match all those different configuration options and just pray it works. If it works, it works. If not, yeah, you need to find a better solution. And if you change anything about the project structure, you need to make sure to update this. How do we solve this? Instead of using source mapping URL, which is just path to any arbitrary file, and the thing is that it can be any host and any protocol. So it can be HTTP, it can be file, it can be FTP, it can be Webpack protocol. Any of the protocols, any URL works, as long as it's valid URI. So how we solve this is that we go to our native friends from C, from I don't know, from Rust, from any other language that is native, because they have something which is called debug ID. Whenever you build binary from your source code, somewhere in this bit mess, there is a unique UID which encodes exactly the state of your code. There is no way that you will ever collide those UIDs, and if you do, you should probably tell someone, because it shouldn't ever happen. So there is a way to make sure like that the distinction is clear between the files. So there will be ever no mismatch. So we need this. We need debug ID. You take the whole file, you go through the UID generator, you create unique value for this specific file that you have for the source map itself. And preferably you do this for source map, because as I said, if you do this for minified source, it can change just by adding a comment, but the bundler will, for example, trim it, and you will be out of sync again. We have the debug ID. This is one of the, I hope it's visible, because this is quite light. You have debug ID. UUID, very, very long number. We add this to the source map file. We have debug ID value now encoded into the source map. So whenever source map is read, it can just find the file with this debug ID. Wherever you put it, it doesn't really matter. It can be any directory, any server, any first party. It's up to you, because this is unique and this is like guaranteed unique. You can find this file. The problem is though that since forever, since the dawn of the earth, error itself in the JavaScript is just a string. Error.stack, if you actually console log this, it's a string. It's a string of some format. It's predefined, but different browsers or different environments also vary slightly, so you need a third-party libraries to parse this. But there is no way to know, if you parse the stack itself, okay, what's debug ID of this path? So for example, what's the debug ID of the path trpc io assets bundle.js? There is no API for this. So this is one of the things that we actually need to bake into the runtime itself. And this is one of the things that we want to change in the spec itself. It's not clear whether we should have something on top of error object or just third-party static method, but just some way to like ask engine, give me the debug ID for this file. I do not care how, just figure this out. And a great side effect of this is that debug IDs are also used for something which is called symbol servers. You can imagine this as just a, I don't know, just hard drive living somewhere, and you upload any files you want, and instead of configuring Sentry, you just go and tell us, hey, this is the URL to our, let's say, S3 bucket on AWS. If you ever need any file ever, like during processing, just go there and look for UID. It will be there. Just guaranteed, it will be there. If you upload this, you just make the contract that when you bundle your app, you'll upload all the maps to this bucket that you pre-configure. And it's basically one-click configuration for source maps. The second problem, which is way more visible for the day-to-day users, and I'm sure all of you have definitely seen this error, you open the DevTools and you see a mess like this. You see undefined is not the function, and all of a sudden, all the lines point to line 1 and column like 20,000 or something like this. The problem is that it's just a nightmare to debug for the post-hoc debugging like scenario, because you would think that if you have this code, you would see something like that maybe function, because we have function maybe, which calls function call me maybe, and we have function call me, which throws the error. You would think that one of those functions is actually the producer of the error. Actually, the engine itself disagrees, and what throws the error is the new keyword itself. If you ask for the token, or like the line and the column, it will tell you that the new before the error is what caused the error. And the problem with this is that if you consult what is the token in the original source, in the source map, it will tell you, yeah, it's new. It's always new. Like, it's new. I don't know what's the function name. Like, you just need to figure this out. And this is the problem that we need to solve. Because when you minify this, how do you know what is, like, what happened even here, right? You have this, this function xy, which throws the error, but the token still points to new error, and you need to somehow figure out how to get the original information back from this. There are 3 ways of this that we implemented Sentry, and keep in mind that all of this is also done by DevTools and other tools that need to somehow pull this information for you. However, for them, they have all the information that they need ever, like, because they have the source code loaded, right? So they do not have like sparse information. They always have full information, so they can use any solution for this. The first one is backward scanning. We have token new at line 1, column 120. And what we do, literally, is we take your minified source, we tokenize it. By tokenizing it, just splitting into the smallest possible pieces, right? So you have again, braces, error, you have new, throw. Those are all separate tokens. So we split them in tokens. We assign them a specific column number, because we can just count. We can go one by one. And we just go backwards, token by token, just praying that we'll find keyword function. If we won't find keyword function, this won't work. This is basically what is the constraint of this first solution. Once you have the function token, we can jump 1 token forwards, because by definition, JavaScript spec says that there are only 2 things that can happen after the function. It's either space and the token itself, the name of the function, or the open braces. So we just gamble and we say, okay, go 1 token forwards from the function that we found, and this is xy. And because we have specific position, we have line 1, column 109, we can go to the source map, and because we already processed all the mappings, we can use this binary search to find this specific token, 109, and we can ask what was the original name. Of course, if it had the original name encoded first, right? Because you have this VLQ, so there is a chance that there was no name whatsoever, like there was no original name. So we'll be left with this XY. So, well, at least it's something, right? We have XY. Second one is color naming. This is even more, just praying that we'll have a good guess. The problem is that it only works if you have access to all the frames, which is the case for DevTools, but it's not the case for all tools. Like some have, some not. Because if you have tool where you just point to a specific position, so for example, you have only access to the information that it happened at line 5, column 1. This is the only information. You are out of luck because you do not have access to all the frames. How it works? We go to the last frame, which is new error, and we want to understand what is the name of the function that actually produced me. So in our case, it's call me. So what we do is we take the frame, we take the top frame, which is new error, and we go 1 frame below. In our case, it will be XY. It's below, top, it doesn't really matter. We go there. We know the position of this column, which is of this token, which is line column 483. And because we have position, we can go to the source map and we can ask it what's the name. It's also just a guess, because what can happen is you can have something like function foo, and then someone reassigns it. Say like const bar equals foo. That's it. And all of a sudden, the name will be bar. It's not foo. And because you just reassign it, it's not there in the source map. So you're out of luck. The same goes if you are, the same happens if you are using something like call or bind or apply or any other function calling methods. It just won't work because it won't be XY. It will be like object call or object bind, something like this. So it's just the best guess. This is the second way that we can do this. And the third one, which is the most complex one, the best one, but it's very hard on the processing, let's say, is AST reconstruction. In order to do this, you need the original code and you need the minified code. So what you do is you take the minified code, you create a whole AST. If you don't know what AST stands for, is abstract syntax tree. You basically take the code that you have and you create the whole structure programmatically of this code. Meaning that instead of just having tokens, like those small tokens, they have meaning now, and they have positions, and they have children nodes, and they have parent nodes. You have this whole structure of the code. Then you do the same for the original code, and you can basically traverse because you have the positions, so let's say that you want to find, I don't know, expression at line 41, or like line 41, column 2, or something like this. You can find this new expression, and because you have information about all its parents and all its siblings, you can create any name you want out of this. So instead of just guessing, we know exactly that we can produce name like this. We can have class foo, which is which has a static method var, and instead of having just a guess, we can know exactly, because we have this AST, that the name is static foo.bar. And this is like the best case scenario. Instead of guessing, we can say that this was a getter on class A in a method foo, not method foo, the getter foo. And the third one is the constructor of class B. So because we have all this information, we can go as deep as we want, because this is the scoping of how the language works. Like there is JavaScript scoping, and you can traverse as far as you want. Thankfully enough, and not really, is that this work is already done in most browsers. And there is an attempt to make this standardized by Bloomberg right now. Instead of creating this ad hoc, we would like to encode this inside the source map itself. Because those scopes, so numbers here, just a quick explanation, numbers here are offset in bytes in the code itself. So instead of having like line and column, you are processing this byte by byte. It's easier this way on the processing. So because they overlap, so for example, you have outer scope which ranges from 10 to 13, and you have inner scope which ranges from 15 to 25, you can imagine it's like inside, right? It's included inside the outer scope. So by processing this data, you can create this whole tree of the structure of the code. And if you need a specific position, you can just pinpoint the place by having this information here. And you're going to have the same searching algorithms to use this. There is an attempt to make this a spec. There is a RFC for this. There is a library which does exactly this, and Bloomberg is using this. And we at Sentry are doing exactly the same, but we are just using, I believe, Rust, and Bloomberg is using JavaScript, I believe. But there is like the proof that this is a working thing, and we just really want to make this standardized. This was the technical part. And now the fun part of source map, not so fun part. The first one is that there is no conformance test. Conformance test is a suite of tests that prove that what you've done is correct. This is a way of testing the implementation of like the JavaScript itself, of CSS, of HTML. All the implementers of JavaScript spec as a language need to follow something which is called conformance tests. It just makes sure that you implemented your language correctly. And this would solve so many issues. Like one of the most prolific is this file paths and URLs. They'll be gone basically because it's standardized and there is only one way to do this. So path resolution. We have this feature at Sentry which shows you code like few lines prior and few lines after where the error happened or where the frame points to. And now we need to figure out how to get this code, because in order to produce this, we need this data, right? So we need to open your original source code, if you upload this, of course. But because there is no spec, nothing stops you from producing source map which looks like this. There is no source content. Source content is literally your original code just shoved into the source map. It's literally this. If there is no source content, you need to go to the disk and you need to find the files. However, the files themselves, for example, here API issues and API components, they can live anywhere, and you need to figure out where. Source root is like a prefix for all those values, so we need to make sure to prepend this. The format itself is not standardized, so there is nothing that make this impossible. You have frame which points to example.com, this bundle. If you open this file, it points to // and some assets bundle.js, but well, it's 2 levels up and you are only one level inside the server. Nothing stops you from doing this. You have file which points to webpack some namespace something. It's perfectly valid, right? The way that we solve this at Sentry right now, there is like 50 lines of Rust heuristics to make sure that we produce correct URL, and quite often we still do not. What is column? This sounds like a trivial one, but this is not what actually happens? You have this very easy code. You have function what, which throws error, and you just call it, but you prepend it with some emojis. So Firefox says it's line 7, column 13. Chrome says it's line 7, column 16. Safari says it's line 7, column 19. Thankfully, Firefox fixed this just last week, so they messed up my slides, but I had to mention this. Right now, it's the same as Chrome. What happens here is that Chrome and Firefox treat this. So Firefox used to treat this as UTF-32, and Chrome as UTF-16 code units. So for Firefox, it was just a single character, like the fire emoji, where for Chrome, it was two separate characters just squashed together to create UTF-32 value. And Safari just decided that it's not what that threw the error, it's the opening bracket, opening parentheses, because I don't know why, no one knows. Off by one, the classic error, which happens everywhere. You can have this code, and there is no way to tell whether the first token is function space and name of the function, or it's a function, and then the second token is space and the name of the function. So whenever you are doing binary search, it's not as simple as matching values exactly. You need to make sure that you include off by one error in your own code, just for the good measure. There is no way to tell that source map is the source map itself, because nothing stops you, nothing specifies this other than the fact that there is literal value 3 inside the version value, inside the version attribute. That's it. And there is, of course, map extension, but you can have any extension you want if you point the file to this. The way to solve this is to create JSON schema, which is standardized. And this way, you can use LSP in your VS Code, in your Vim, in your Emacs to get an auto-completion as well. OK, so what's the future for this? The first time that the spec was created was in 2009 somewhere. There is no really way to tell because the history is kind of blurry here. It was created by Google, I believe. The second revision was 2010, and we know this by a very specific reason, which I'll talk about in a second. Revision 3 is since 2011, and hopefully not a revision 4, but rather updated revision 3 or something that's workable will be done quite soon. If you ever worked with source map, this is your whole spec. This is the only thing that you need to use, and you can use. It's 9 pages long, Google Docs, created by an employee from Google in 2011 or 2010. This is the only thing that you can use, really. Thankfully, Armin from Sentry translated this, and we have very nice formatted code right now. So how to move this forward? Around April or May this year, there was a TC39 tooling meeting. There is a so-called work group around tooling, which means that anyone can join. And if you have any problems with any tools around JavaScript ecosystem, you can go there. It's every month. And you can just tell them what's your problem and what's your idea to fix this. We decided that source map is way too large because all of us are using it every single day. And it will only grow and grow because everyone is using, everyone is trying to push either DSLs or TypeScript or compilers, minifiers. So we need a way to make this reverse mapping. And what happened after about a month or two, we created something which was called TC39 Working Group for Source Maps. And we went to the TC39 and told them, hey, this is quite big. Can you actually take this under your umbrella? We would really love some help making this official. And this is the name of the official group. It's called TC39 Task Group 4 right now, which is a group responsible for making source maps actually workable for all of us. And the good thing is that if you really want, you can actually join us every month. There is a meeting. There is open forum. You can join our Matrix channels. You can read through all the RFCs, all the spec. If you have any ideas or something that bothered you working with source maps, you can now go there. You can complain. You can maybe show your ideas. So if you ever want to evolve JavaScript or just work or take a part in evolving the language itself, this is probably your good way in to the world of TC39. Thank you.